somebody, like you go to a doctor or anything, you get in there and they start talking to you, you forget everything you want to ask them. And I left and I was like, I don't, they ain't answering my questions. But I'll just try to figure it out myself because I don't have to, because I took us like 2 weeks to be able to meet each other and then left and didn't have anything. And it was great. I loved it.
Well, here's the scoop. So you had your test out there, right? And in Canvas, I had put together some problems for Chapter 8 that I wanted you to do. And unfortunately, I forgot to publish them. So there were 3 problems for Chapter 8 that I had hoped you would work on over the week, but you didn't even see them. Because when I went to look on Canvas tonight to see how many had gotten done, it wasn't in the grade book because it was never published. So I'll publish those this week. So I thought what we'd do is we'd go ahead and start with just running through maybe 3 practice problems in Chapter 8 to kind of get us back up to speed there. And then we're going to go ahead and dive into Chapter 6 and go ahead and cover Chapter 6 tonight. And here's my thought process on that. I had mentioned earlier, the teams there's only one team, and that's an individual, that's really on task right now. And so because that person is the only one that's on task, you guys really need to play some catch-up here in the next couple of weeks. And so next week, I will just devote the class time. I'll be here, and I'll make appointments with each team for you to come in, and we'll go through where you're at with the project and talk about what you need to do. And I'll plan for an hour with each team that's here in class, okay? And then the 2 that are online, I've just been talking to them when it's most convenient for them. But I'm thinking that way everybody from your team that's physically here should be able to be here for that. And that way maybe you can make sure that everybody's on target, know where you need to go, and make sure that you're not coming to the end of the semester and not going to pass the project because you're not going to get where you need to get to with it. So let's make sure we do that. Corey, can you hear me?
Yes.
Okay, great. And let me...
Are you going to let me know whenever you're doing the conference?
Say that again?
Are you going to let me know whenever you're doing the conference for the project?
Yeah, in fact, let's just decide that right now. Let's see, Brian is on your team, right? Corey's on your team, okay? Corey, how about, should we just plan for 6 o'clock with that team and 7 o'clock with this team?
Yeah.
Okay. So you guys don't need to just show up at 7. You don't need to be here before 7 o'clock, and we'll go with, Corey will go with your team at 6, okay? And then that way...
On Monday?
What's that?
6 on Monday?
Yep, 6 next Monday. I'm not saying that you won't work on your project between now and then, but we'll sit down as a group and go over the project at that point in time. All right, so let's do a couple more practice problems for Chapter 8, and then I will hit the publish button for that homework assignment that was supposed to be out there. And you can kind of refocus on those again. I kind of also feel like there's probably a lot with getting the test done. That was kind of a time that you needed to take outside of class this week too. If you have a textbook with you, go ahead and pull it out, and let's look at the couple of problems at the end of Chapter 8. There's not enough room up here to be handy. The first one that I want to look at is going to be problem 8-7. Okay. And it's going to kind of remind us about what that spreadsheet was, what we were using that spreadsheet for, and how we can make some decisions based on information from that spreadsheet. Okay. Go ahead and open up that spreadsheet.
What page is it on?
A bunch open here. All right. I know I need to share the desktop here. Let me do that. Set up. Okay, Corey, are you able to see the spreadsheet that we're going to work with?
Yes, I'm trying to find my book.
Okay. All right. So 8.7 basically says, since deregulation of the airline industry, increased traffic and fierce competition have forced global airlines to re-examine the efficiency and economy of its operations. So as part of the campaign to improve customer service in a cost-effective manner, Global has focused on passenger check-in and operations at its hub terminal. For best utilization of its check-in facilities, Global operates a common check-in system. Passengers for all Global flights queue up in a single snake line, and each can be served at any one of several counters as clerks become available. Arrival rate is estimated at an average of 52 passengers per hour. Okay, so our arrival rate is going to be basically the 52 passengers per hour. Do you remember what variable that is, guys? The R sub I. That's going to be our arrival rate. During the check-in process, an agent confirms the reservation, assigns a seat, issues a boarding pass, and weighs, labels, and dispatches baggage. The entire process takes an average of 3 minutes. What's the 3 minutes represent? Nope. Nope. You're just reading off the... Harley, what do you think that represents? So it takes 3 minutes to complete the activity. Average T to P, average time to process, okay? So we're going to use then the 1 over the T to P for the service rate of each server, all right? So as you're reading the problem, when it comes across something that's telling you that the average process takes, that's the T to P. That's the average time it takes to complete that particular process, okay? Then it tells us that agents are paid $20 per hour, and Global's customer relations department estimates that for every minute that a customer spends in a waiting line, Global loses $1 in missed flights, customer dissatisfaction, and future business. And so the question is, how many agents should Global Airlines use to staff its terminal, okay? Which is a pretty relevant question, right? If we've got that information, surely we can get this figured out. All right, so in order to figure that out, we have to solve for C, right? We're trying to figure out how many servers we need to have, okay? And so we kind of have to have a starting point, right? And kind of one of the things that you have to understand is that we're always saying we're assuming we're dealing with a stable process, which means that we at least have to have enough servers to meet the current demand, right? And so that means that our utilization of our servers has to be less than 1. Because if they're more than 100% utilized, then our queue is going to continue to build and build and build, right? Everybody agree with that? Okay, so if our utilization is the inflow divided by capacity, okay, which is one of the things we talked about in Chapter 8, we know that our inflow rate, we just talked about, was 52 passengers per hour, okay? And our capacity capacity is going to be the throughput for one server times the number of servers that we have. So we need to make sure that we have at least enough servers to meet a utilization rate that's less than 1. So we would set up an equation that then where we talk about utilization, and we would say that our inflow rate divided by, maybe I'll just do it like this. I'll do inflow over capacity, right? Inflow divided by capacity. Has to be less than 1. Okay? And we know that our inflow is 52 an hour, and our capacity, I'll just do it in the summary. And our capacity is going to be our number of servers times the throughput rate for the process. Okay? So now we're saying that that's what has to be less than 1. Okay? And so our average time to process, we said, was how many? How many minutes? 3. So how many can we process in an hour? 20, right? So 20 is our throughput rate of the process. Okay? So basically what we're going to say is 52 divided by C times 20 has to be less than or equal to 1. So then we're just going to solve for C. And so we're going to set it equal to 1. And when we solve for C that way, we find out that it has to be at least 2.6 servers, which means that we're going to round up to 3. Okay? So I know the thing about that I find challenging about this book and that I like about this book is it makes you think about information that you're given, and you have to apply it in different ways, right? Because we're kind of used to, in some of our classes, being given a formula, shown an example, and then just working that exact example, right? And that doesn't necessarily help you when you go into the real world, right? You're going to have to be able to take pieces of information and put them together in different ways to try to solve problems, okay? So that's kind of what we're trying to accomplish with this class, is saying, okay, we're given some pieces of information. What do we know about business as a whole? How do we transition that into something that we can find useful? Okay, well, in this example, we're going to look at then if I have to start with a minimum of 3 servers, okay? So I have to start with 3 servers, and my cost per hour for my servers is $20 an hour, okay? The cost of wages per hour, and is that on the wrong side? Okay, so my cost for 3 servers is going to be $60. Okay, is this an infinite or a finite queue? Do you remember tell me what the difference between an infinite and a finite queue is?
Is an infinite that you can keep on. I know it's even, of course, infinity means forever. So I think you can keep on adding more customers, though.
So in the snake line, did we have anything that said you can only have so many people standing in line? So that makes it an infinite type of queue. Okay, so it's going to be infinite. And we knew that our arrival rate was 52 per hour, and our processing rate was 60 per hour, right? We figured that just a second ago, okay? And so that being said, right, that's some information that we have that we can transition then into our spreadsheet, okay? So we're going to come over here, and we're going to say we're going to start with 3 servers, and we're going to say that our arrival rate is 52, and our service rate of each server 20, right? The service rate of the whole process is 60, but now this is going to calculate it for us because we're saying how many servers we have. Okay? All right, so that being said, I can look at this and I can say, well, on average, people wait in line 4.932 minutes. So I can come back over here and I can say that they wait in line for 4.932 minutes, okay? And we can say that the average waiting, that's the average number of queues, 4.932. The average waiting time is 0.09486. What is that of, though?
An hour.
Of an hour, right? So if we were going to change that to minutes, how long do they actually wait?
5.4 minutes.
Okay, so they wait for 5.4 minutes. Okay. What's that?
Screen's not showing.
Oh, that's okay. I'll type it over here for a quick second, and then I'll pull it back here in just a minute. We'll keep looking at this. Okay? So we want to know what our average queue length is, and we said that that was 4.93. Okay, you can see that from, if they point to the screen. That's very helpful, isn't it?
Yes.
So it's right here, 4.932. And we have our average waiting time. And then we need to come up with our waiting cost per hour. And basically, if we go back to a problem, how much would it tell us that it costs for the waiting? Global loses $1 in missed flights, customer dissatisfaction, future business for every minute. So how much is that per hour? 60, right? So our waiting cost per hour is 60. And really that's all that we're tracking on this particular problem. Okay? So we're going to end up and we're going to say that our total cost then for 3 servers is going to be the cost of the wages and the cost of the waiting time. Okay? So, and this is our queue length that we're putting in here. Right? Everybody tracking with that? So I put out this template for you to help you with the problems that you're going to work for 8.4, 8.5, and 8.6. Okay? And I did that because you need to systematically think about, when you start to think about the cost of the service, you need to see whether or not they're giving you cost of wages, cost of equipment, cost of lost sales, and cost of waiting, right? And so your cost of wages is going to be the number of servers times how much they are per hour. Your cost of equipment, if you remember when we worked on a phone line example, we said that each additional phone line was $5, right? So you would have to add in how many additional phone lines you would be adding, okay? And then your cost of lost sales is going to be given to you by those that are blocked. So that happens when you're in a finite queue, not when you're in an infinite queue, right? You have somebody that can't get into the system, and a lot of times your problem is going to tell you then what that cost is associated with. And then the cost of waiting is going to be, for those people that have to wait in line, the longer they have to wait in line, you're going to, according to this, you're going to lose $1 a minute for future sales, okay? And so you can kind of come back in here, and you can come up with whatever works best for you. It often is easiest for me to be systematic and think and look at the problem, because these are the 4 categories that we're dealing with in terms of cost, and to look through the problem and go, am I talking about 1, 2, 3, or 4 different things in this problem, and then make sure that I calculate the cost accordingly for those 4 categories, all right? And then this problem has this twist because you have to recognize kind of where to start. And you wouldn't have to. You could start with 1, 2, 3, and you work your way through it. But it wouldn't make any sense to start with less than 3 because you're not going to have enough to actually to process, okay? So that's think that if we have 3 servers, our total cost is $356. Okay, so I can come back to my copy of performance and say, well, what's my total cost if I go to 4 servers? Okay, well, if I go to 4 servers, my inventory becomes 0.65821. And Brady, would you calculate then our average waiting time in terms of an hour, 0.01266? Okay, so now, so this is at 3 servers, right? That's what we had at 3 servers, and then this is what we're going to have at 4 servers. So our waiting time is 0.75, and our queue length is, she said, as though she can remember. Yes. So I'm going to bring it back over. Change this. Instead of the cost of waiting for 4.93 people, it's going to be 0.6582, right? And so my cost goes down to about $99 in total. I also have to change this though, don't I? That has to go to 4 services, $119 in total. So I have to change those 2 pieces of information when I'm looking at 8.7. Okay? And then if I go to 5 servers, I can come back and take a quick peek and say, well, what happens then? I'm go to 5 servers, and my queue length goes to 0.16104. And you want to calculate the other for me?
0.003.
0.003.
0.18.
Oh, I'm sorry. This should be what?
Oh, 0.18.
0.18. Okay. So you can see our waiting time as we keep increasing our servers goes down. I'm going to go to 5 servers. We were at 119 with 5 servers. And then 0.161 here. It's $110. Okay? So still lower. Okay? Last but not least, we'll take a look at 6 servers. Okay, 6 servers, I don't even have to figure out, well, I'm going to be waiting less. It actually goes up more because the cost of the server goes up more. So 5 servers is our ideal solution. So there's no like magic bullet to solve these. You just have to think about the information that you have and apply it to with information that we know. Okay? And try to kind of work through it that way. Most of them don't have like this little piece of the puzzle though. Okay, so that's a little bit added twist to this problem where we have to think about that utilization before we ever even start. Okay? From a conceptual standpoint, we're gonna work on just a couple of problems here from a conceptual standpoint. So for 8-9, I want you to just listen, and then we're going to answer the questions at the end. So Burrito King is a new fast food franchise that has had problems with its drive-through window operations. Customers arrive at an average of every 30 seconds. Current service time is average 25 seconds. So it's a stable process. We can serve them faster than they can arrive, okay, with a standard deviation of 20 seconds, okay, until we get that variability, and then maybe we can't with that variability thrown in. A suggested process change when tested results in an average service time of 25 seconds, okay, so that hasn't changed anything, but our standard deviation has gone from 20 seconds down to 10 seconds. So assume that no customers are blocked or abandon the system. As a result of implementing this change, will the average waiting time in line increase, decrease, or remain unchanged? We take variability out of the system. What happens to our average waiting time?
It decreases with it.
It decreases, okay? As a result of implementing this change, will the average server utilization increase, decrease, or remain the same? It does. Did everybody get that? It remains the same because we didn't add any more throughput to the process, right? It's just those customers that are coming through are able to get through faster. We didn't say that we weren't having any blockage before, so actually improving that improves the wait time for the customer, but it doesn't mean that we have more customers coming through, so utilization doesn't change. All right? And then 810 is kind of along that same line. So 810 says, ZV Ranger is a seller of industrial products. All purchases by customers are made through call centers, where Ranger representatives take orders. Currently, they have 350 warehouses in the United States, each with its own call center. Customers call one of the call centers and wait on hold until a representative at that call center becomes available. Ranger is evaluating a switching system where customers will call 1-800 number from where they will be routed to the first available representative in any of the call centers. If Ranger installs the switching system, will the average waiting time of customers increase, decrease, or remain the same? What do you think? So before, I might have had 10, we'll just make it simple. I might have had 10 call centers, and if I called in, I was calling a specific call center, okay? And so then there were representatives there that would take my call in the order that they received it, right? Now I've got these, we'll just say, 350 warehouses, and when I call, it's going to be routed to the first available, of all of those. So does that make it wait more or wait less? So as the customer, I end up waiting less because I have this pooled, we're pooling that and allowing it to go to wherever the first available person is, as opposed to anytime you segment, it's just like when we talk about inventory in warehouses in a company. If I am pooling my safety stock, I have less safety stock because I'm concentrating that variability into one pool. If I segregate that variability, everybody carries more because they're accounting for that variability within, and it's the same thing, it's that same relationship with waiting time. Okay? So if we segregate it out, so as an example, if you went to Walmart and Walmart had one long line and you just went to the first available checker, you would actually wait in line less time than what you do today, right? Because today you divide it out and that variability is spread out and you're dealing with different variabilities for each checker, right? If we combine those checkers all into one pool, you actually have less time that you're going to waste.
It's kind of like, what's that thing called? TJ Maxx, maybe something like that? You wait.
Yeah, it's like in a snake line. And you can say that right first register. Yes, that is exactly right. That's exactly right. There's a bookstore up there that does it too, I think, in that same
but yeah. I guess that's one place I can.
Yeah. So, and they take that same approach. So it depends a little bit, on what you're trying to accomplish. If you're focused on trying to get your customers through in a speedier time, that snake line can be kind of convenient or can be a good thing. But if you think about trying to manage that from a flow perspective at Walmart, it could get kind of ugly, right? It could have a long line of people waiting to get to that next register.
I think they like their locker checkouts too, just because every checkout has candy and things. And
right. And you've got more time to stand there and look and think about whether or not you want to buy that magazine or that candy bar. Or if you've got small children, they want to screen for the best food.
Yep.
Yeah, it does. It does. Yeah, there's a tactical reason for that. And in fact, when we worked at the university bookstore, that's one of the things that we talked about with them. There are different approaches. And what they wanted to do then is have merchandise beside the line that you were walking through so that you had the opportunity to look through it. And some things where we thought, well, it might make more sense if, from a pure efficiency standpoint, it might make more sense, but from a customer contact with, product, maybe it doesn't make more sense. And so you have to balance those things. Okay? So those, I wanted to just do a kind of a cost problem here. You're going to do, again, when I publish this, you'll have this template that you can use. You don't have to use, but I think it's a good thing to help you kind of think through the 4 different costs and then make sure that you're aware of how you're going to use those 4 costs. And if you get stuck, you can go back to, we did some other examples last week, and so you can go watch that video that we did last week as well. Okay? All right. That being said, let's go ahead and flip over and do chapter but I think it's our best choice based on where we're at for the semester. I'm kind of feeling this project out to see the due date. I've got one student who's kept up, and in the past I have not divided them out as much. I've kind of only had two, like a midterm and a final project. But what I found is students weren't really getting with it and getting after the project until like the week before the midterm. And I need you to be started on it earlier in the semester. But I'm still not sure that it's been as successful. I think you're thinking about it more. I just don't know that we've necessarily gotten it resolved. And so kind of be thinking about that, giving me some feedback at the end of the semester about what might work better in terms of the breakdown of the project. Okay? Because again, I find it interesting that I have students that can get A's on the exam, but yet when we go to apply the material to the project, it's a different thing, right? And so it's the same kind of a deal that we're talking about where you've got pieces of information, and if you're just asked to kind of regurgitate, you can do that. But if we're asked to say, how do we apply it, I want to make sure that we're getting the application in a real-world situation. So again, I think that's what I think the value of that project is. And so, but I'm open to feedback. I don't know that it's working real well. You guys can probably tell me that having kind of the one online team member, that's probably not working real well for you, is it? So for the online folks and for you,
it's just harder to get them involved. It is.
Yeah, I feel bad for it, but it's hard.
Well, I think maybe when we get to the Chapter 5 piece of it, that's what we're going to want to break out for them, because you'll have done all the fundamental pieces, and then maybe they can step into some of the Chapter 5 or Chapter 8 pieces of it, okay? But, that's one of the things that I think about is I don't know that that has worked as well as what I would have hoped. So, and it's, again, I don't think that's anything against any of you or them. I just think it's just maybe not the best approach to go for there. All right, so I wanted to open up chapter 6. And this should seem really familiar. Do y'all remember EOQ from 343? Sort of. Yeah, that's why I feel better.
Sure.
I remember everything about it.
You don't remember anything about it?
I remember everything about it.
Oh.